Hi, this is Ozer, and this is my project for MSDS 692, PracticumOne, San Francisco Restaurant Inspection Score Prediction. Having worked in the service industry, I've always been fascinated by the structure and the scoring aspects of the restaurant health inspections. For my practicum project, I thought I could use the restaurant inspection health scores dataset. In this presentation, I'm going to highlight some of my key findings, challenges, and a few tips and tricks I picked up along the way. For analysis, there are 7 notebooks, 6 Python and 1 R, with few curated datasets as an output. All are available on the project's GitHub page, Scoop version 2. To accompany the project, I wrote a Medium blog for the online presence requirement. The link is posted below. The blog post has all the links. The food safety program in San Francisco enforces health code regulations. To enforce these, food safety inspectors inspect over 5,000 locations in San Francisco, including restaurants, bars, markets, bakeries, push carts, stadium food facilities, and any other facility that serves food to the public. The coronavirus outbreak brought health and cleanliness as the top priorities in our everyday lives. As the restaurants start to open up, they are tasked to update their approach to cleanliness. A list of new guidelines was published by the Department of Health mandating additional measures. But the initiative creates a logistics issue for the health department to put in a plan to monitor and enforce these guidelines. This study aims to analyze inspections over time and produce an acceptable prediction rate of 90% when inferring a score and assist San Francisco Department of Health prioritize their resources for the post-COVID-19 inspections. One of the reasons I chose this subject was the availability and the social nature of the data. The dataset is from DataSF and is part of the Open Data Standard with an API for access. API access can be handy when creating a continuous data pipeline for future work. The dataset is posted in a single tabular table with 54,000 rows. It's currently set to update weekly. However, it has not been updated since November 2019 because of the citywide shutdown for COVID. Although this is a semi-curated dataset, there have been no efforts from DataSF analysts to further clean the open text fields or aggregate. There are a few simple derived columns that were created by default during the joins, and none were useful to me. This made prepping the data especially difficult and time-consuming. To understand the data and its components, I sliced and diced it every way possible. The granularity was at an inspection level. Although this helped with aggregating up, I had to create every predictor from scratch using derived tables. Some of the decisions I faced were banal, such as what's the best way to treat nonce or geocode missing latitudes and longitudes. And some were unique, such as splitting inspection ID to parse business and inspection dates. One thing I never thought of and caught by luck was the business postal codes. San Francisco City starts with 9 only. Missing zip codes in the dataset are typically expected, but I was surprised to see incorrectly entered zip codes. Chart shows the distribution after the extensive formatting. For the incorrect zip codes, some records had latitude and longitude available. And I did a spike on reverse geocoding, which is also available in the explanatory analysis notebook. Another challenge was deciding how to slice the data geographically. The only usable value in the original set was the street name. When I first moved to San Francisco, I was told that the scenery changes with every street. So as you turn, you will either see 100-year-old updated Victorians, brand new condos, or completely dilapidated buildings, all within range. Here is the chart of the most and least sanitary streets list. I aptly called it Streets of San Francisco, the Delicious and the Dirty Dozen. The vertical line is the inspection score median. It's Nice to see street level info, but I need to know more. One disadvantage of my dataset was that it's small and has only 3 years worth of data. Although there are roughly 50,000 records, data is at an inspection level. The interquartile range of the inspection score versus risk category was interesting and formed the basis of my future generation. If you like, you can read the reasoning in my blog. Next, geocoding for the missing location information. A tutorial I found on Medium recommended OpenK Geocoder. The package was intuitive and easy to use, however, it has API limitations. I found an alternative package called GeoPy that worked much faster with no limits. Formatting data for the API call was a long and arduous process. However, regex was a big help. It was quite difficult to come up with a single regex that would cover all cases, but I tested enough to make sure I covered most. Also, instead of sending the entire dataset for location generation to speed things up, I created a data frame with business IDs without location, which lowered my number to 3,500. So imagine from a raw data of 55,000 to a mere 3,500. Not too bad. Well, it still took over an hour to run. A tip here is to make sure staying logged in to your instance during the entire run so you can catch accidental login refreshes. Finally, I added a new field for neighborhoods. The list was compiled by mapping the business postal code field using a dictionary built from the SF Department of Health's website. In pre-processing stage, my goal was to start creating features that will help me infer a score prediction. Since the dataset was at the inspection level, it made sense to learn more about the inspection types and their frequencies. This enabled me to aggregate data strategically. As soon as I had the aggregated data, one thing I couldn't resist was to plot the best and worst of SF restaurants by mean score. This is the map for the best list. If you prefer an interactive version or the map for the worst, then head over to the project's GitHub. It's worth noting that the best is truly the best. These restaurants have never been dinged for any violation, ever. They have a mean of 100. Browsing through the data at neighborhood level helped me see what was available for future generation. By using the only numerical column, my classifier, and by aggregating inspection visit information at a business level, I was able to drive a variety of predictors. Next, violation description field piqued my interest. Since one of my goals is to show as many techniques as possible, I decided to dig deeper into the contents of this field. Here is the word frequency result of the violation description corpus. Needless to say, seeing the words vermin and food side by side is a bit eerie. I had the inspection data available, so I created 3 time series charts, daily, monthly, and yearly distribution of the words. I think this type of plotting helps to get a sense of sample density and sometimes uncover interesting insights. In the yearly figure, there was a significant increase from 2017 to 2018. I think just like any time series data, this analysis can benefit from more observations. For my machine learning algorithm, I picked a random forest, and there are 2 main reasons. First, the inspection scores dataset shows homogeneous data that is linear. And second, scores are a sensitive subject for the restaurant owners. Therefore, my method should be transparent for legal reasons, and my results should easily be transcribed to be shared with other entities. The results for the decision tree and prune tree were identical, and the random forest was a bit higher. Also, normalizing did not have any effect on the results. I looked into why the pruning may not improve the results, and there can be many reasons. To test, I changed the CP value manually. However, accuracy did not improve. I am interested in mostly the D, 4s, and the C, 3s, the scores. Although the rate is acceptable for D, the error rate for C is a bit significant. However, an overall 90% accuracy is not too bad. I also tried k-fold cross-validation to optimize my model's complexity. I cover the details in the blog. After a little cleaning and reformatting back to the letter grade, I merged back my original dataset and then mapped a random 50 restaurants with a predicted letter grade of D. Top 50 because I think that is the maximum number inspectors can cover in a day, especially when not considering the distance between the facilities. Some final thoughts. First and foremost, work with everything small. Small data sets, sampled files, not only it runs faster, but also it is easier to comprehend the results. You can utilize progress bars for long running queries. It helps pass time. The dataset needs more features and even more data. For this reason, perhaps training on a larger set such as New York or Portland especially, could have been better. However, this would have required a significant regex effort since the data collection formats are vastly different from each other. Finally, I was able to reach my goal of 90% accuracy in predicting post-COVID restaurant inspection scores. I think there are enough restaurants that are historically persistent violators of the health code. Inspectors can start their inspections with the list on the map. Thank you.